what we just learned in the lecture about this idea of hypothesis testing, right? So basically, we know now that somehow or other, this idea of hypothesis testing is kind of related to this confidence interval and so on and so forth. Somehow or other, that the two of these are connected. Okay, so we've been playing around with confidence intervals so far. We've been trying to predict what a population mean really is without sampling the entire population, and only sampling a small number randomly from that population and using that to estimate what the population mean. And also using that to create this thing we call a confidence interval, which gives us an idea of how certain we are that the mean is at least within a certain range. Okay, in a way that we can quantify what our level of certainty is. Sometimes we want to be 90% certain, sometimes we want to be 95% certain, sometimes we want to be 99% certain. And the way that we're adjusting for that is by making that range wider. The wider it is, the more confident, the higher level of confidence that we have that we really captured the population mean. Well, why do we want to do that anyway? We want to do it usually because we want to know what the population mean is so we can compare it to a different population. Okay? For instance, we might want to be interested in what the mean blood lead levels are for children between 5 and 7 in the Bronx. They live in a whole older housing. You generally it's a poorer areas. A lot of children living in poor areas of the city. We might want to compare what the mean blood lead level is for children in that environment to say children in the city as a whole, in the country as a whole, or maybe even compare it to another country. Okay, so we might be interested in knowing. We're not going to sample. Well, actually, we do now, don't we? We test every kid now in school, so we could actually know an entire population. Okay, but let's say we didn't, for instance. Okay, let's say that we wanted to know for the Bronx, and we wanted to sample. We could only afford to perform blood tests for 100 children in the Bronx. So we randomly sample 100 kids in the Bronx, and we find the average blood lead level for those 100 kids. Well, we know 100 is a pretty good sample, right? Reasonable size sample. And we have a pretty good idea that that should be a pretty good estimate. But we want to quantify that. So we quantify that by creating this confidence interval. Okay, so now let's say that the average comes out to be 5 micrograms per deciliter of blood. Okay, now that's what we got for our sample, but our confidence interval, based on the variability, some kids might be 3, some might be 12, and so on and so forth. Based on the variability, we predict that our 95% confidence interval is 3 to 7, for instance. Okay, so now we're 95% sure that the average blood lead level for children in the Bronx of that age is between 3 and 7. Well, now, if I know that the average blood lead level for all children in New York City is 2, I can say with some level of certainty, like 95% certainty, that the average blood lead level for children in the Bronx is different than it is for children in general in the rest of the city, assuming that I know the actual real population average for the rest of the city. Okay, so that's kind of the way you might want to look at this, that this 95% confidence interval gives you a way to decide whether or not you could exclude another population from having the same average as that population. There's some ways that some ways that you might say to yourself, well, this is not really the best way for me to use this, and we're going to start to find better ways to use this idea of the variability of a sample and the variability and the mean for a sample, and how to figure out whether or not two populations are really the same or different. And one of the ways that we're going to do this is we're going to use an idea called hypothesis testing. We're going to create a hypothesis. A lot of times in science, they do this anyway, don't they? They create a theory. They have an idea of how something might be or something might work, and then they go out and they try and test that. Okay, well, in statistics, we do something very similar to that. We create a hypothesis, okay, and we say to ourselves, okay, our hypothesis generally is that the two populations really, because what are we usually trying to prove? We're usually trying to prove that two populations are different, right? That there is some that there is some reason to intervene in a population to protect those children, say in the Bronx, because they have a higher blood lead level, we suspect. So usually we're trying to prove that their blood lead level is different than children in other populations, in another population that we're referencing it to. We're trying to prove that a drug works. We're trying to prove that people that take the drug have a better outcome than people that take a placebo. We're trying to show that they're different. We're trying to show that an intervention, let's say a dietary education for diabetics, is going to improve their outcome, compared to diabetics that don't get nutrition training, right? So we're looking to show a difference. Well, ironically, the way we do that is by first assuming that there is no difference, right? We create a hypothesis that says there's no difference between the blood sugar levels for diabetics that have gotten trained in nutrition and diabetics that haven't gotten trained in nutrition. There's no difference. They're the same, right? Blood lead level one, group one, is equal to the blood lead level or the blood sugar levels of group one and two. They're both the same. That's called a null hypothesis. We always start with a null hypothesis. There's always an equal sign involved in that null hypothesis because by definition we're saying that there's no difference. The difference is null between those two groups. Then we're going to apply what we know about samples and variability, standard deviation, and so on and so forth to prove with a level of certainty that we're going to choose 95%, 90%, 99%, that we're going to choose to be able to reject that idea that they're the same. We're going to prove with that level of certainty that they're different so that we can reject that null hypothesis and accept that they are different. We're going to call that difference the alternative hypothesis. Null hypothesis is that they're the same. The alternative hypothesis is that they're different. Okay, so from now on, we're going to be using the null hypothesis and the alternative hypothesis until we're blue in the face. We're going to be nauseous with those hypotheses by the time we're done with this semester. Okay, but that's really what this is all about. We're going to structure this idea of understanding how samples work and how variability works, and we're going to structure it in a way that we're going to be able to use it to prove that our null hypothesis is wrong, that they are different, so we can just toss it aside and reject it. Sometimes we won't get to that level of certainty. That doesn't mean it's not true, right? Like in other words, if I can't say if my benchmark is I want to be 95% certain, that's kind of another way of saying that I'm willing to have a 5% risk of being wrong if I'm 95% certain. If I can't prove with 95% certainty that two things are not different, that they're different, that doesn't necessarily mean they're the same. They just mean that I haven't proved it, right? So sometimes we'll wind up rejecting that null hypothesis. Sometimes we won't have enough data, and we'll fail to reject the null hypothesis. We almost never are going to be in a situation where we're proving the null hypothesis because that's not really what we're after, and that's not really what this is structured to do. So we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. We never wind up proving the null hypothesis. It'd be very difficult to prove anyway, right, that they're the same, right? Because we could always happen to wind up with a sample that suggests that they're the same, for instance. Okay, so at any rate, so that's really what this is all about. Let me make sure we're still muted and we're recording, and we sure are. Okay, so we're going to go back and we're gonna start working on some of these things again, and we're gonna work our way into these hypotheses. Okay, and we're gonna start with looking at the idea of exercising our understanding of the confidence interval, and when we use the z-test and when we use the t-test. Now I'm going to upfront say that if you use the t-test, you're never wrong, right? In other words, if you have a sample of size 25, that's a small sample. If you don't know the population standard deviation and you have a sample of size 25, you should definitely use the t-test because the only place you're going to get the standard deviation from is from that small sample. Small samples usually introduce some level of uncertainty in the standard deviation. If you know the population standard deviation for some reason, that's great. You know exactly what it is. There's no uncertainty. You could use the z-score, right? But if you have a sample of size 25, small sample, you should really be using the t-test exclusively for that, because that gives you a bigger number than, say, for 95% confidence, 1.96, and it makes up for that uncertainty. It makes your confidence interval wider, automatically makes up for that uncertainty. Of course, the t-test, depending on your sample size, you're going to have a different t-value that you're going to use when you calculate it, right? So that's the only difference is that the sample size determines what the size of that t is when you take your t times your standard error and add and subtract that from the mean. So now, how about if we got a sample of size 29? Well, still should use the t-test, right? How about if you have a sample of 100? Well, remember we were talking about if it's a large sample, you could use the z-score instead of the t-test? That's only a convenience. The right answer is always the t-test. The more accurate answer is always the t-test. But if it's a very large sample and we want to save some time, we might just use the z-score, use 1.96. But that's an estimate. We're cheating when we do that. It's an okay cheat for a big sample, but we're cheating. If you want to be sure, use the t-test. How about a sample of 1,000? We don't know the population standard deviation. We know the sample mean and the sample standard deviation. Should we use the t-test or the z-score for a sample of 1,000? Well, we could use the z-score as a convenience, but the right answer is always a t-test if it's a sample and we don't know the population. If it's a sample size of 1,000. In fact, this not so much today, but next week we're going to get back into using SPSS and some of the software to calculate standard deviations, calculate confidence interval, calculate t-scores, and so on and so forth. We're going to use software to do that. SPSS always uses the t-score. It doesn't matter if the sample size is 10,000, if the sample size is 20,000. If the sample size is one less than the population, it's going to use the t-score always, right? Why? Because it's built into it and it can automatically do that without wasting a lot. Even if the t-score comes out to be 1.96000001, it'll still use that instead of using 1.96. Why? Because it doesn't, it's no more elbow grease involved in it doing that than using 1.96. It's already built into it. It's a machine. It's going to calculate it. Of course, for you, if you get a very large sample size, you're going to be tempted to use the z-score, and it's going to be okay. But the real answer is always a t-score. The only time the real answer is not the t-score is when you know what? The population standard deviation, sigma. Then the z-score is the right answer, right? Can you use the t-score in a situation like that? Yeah, you can, but you're kind of cheating yourself a little bit. Why are you cheating yourself a little bit? Because you could have used 1.96 because you knew the population standard deviation, but you didn't use it. So you wind up, if you're using the t-score, you wind up using a number that's going to getting a confidence interval that's a little bit wider than you really need, right? A little bit less accurate than you really need it. Is that a terrible thing? No, it's pretty conservative, actually. That's not such a terrible thing. So using the t-score is never really a mistake, right? If you know the population standard deviation, you don't need you need to use the t-score, and you're going to come out with a more conservative answer. You're not going to get you're not going to get your most advantageous result, but it's not such a terrible thing after all, because it's just going to be a more conservative answer. You're going to be less, in other words, it'll make your confidence interval wider. It'll make it a little less likely you'll be able to reject your null hypothesis, just a teeny bit less likely, right? So there's a little bit of a disadvantage to using the t-score when you know the population standard deviation. But number one, it's not going to come up very much in real life because you're very rarely going to know the population standard deviation, and the cost of it's usually pretty small. So when you use the software, and trust me, in the future you're going to very rarely going to be calculating this by hand. You're going to be mostly using software like SPSS and SAS and so on and so forth, and R, for instance, to calculate this stuff. And in those situations, most of the time it's going to be using the t-score automatically. Okay, so that's let's start with that, and let's go back. Some of this is going to be review. because we're going to reintroduce this and work this back in so we all understand how this works out. And we're going to ease our way into this idea of hypothesis testing. Okay, so I have a document on Blackboard called Lab Exercise 1, November 2nd. Okay, and the first problem there is, let me make sure you guys online are okay. Okay, you guys okay there? Online? Yes? Okay, good. Okay. Okay, so let's look at this first problem. Suppose we want to know the true population proportion of Irish Americans who approve a wider representation of all groups in the St. Patrick's Day parade. But as a random sample of unfortunately starts off with a point proportion. I would have not liked to. I would have liked to have 2, 3. You want to know something? Here's something I changed some of these things. Hang on a second here. Did I misidentify these things? Hang on one second here. It's not what I'm thinking of. I'm going to say T-score. 1B. Oh, okay. I changed the numbers on these, and I meant exercise 2 to be exercise 1 and exercise 1 to be exercise 2. So I'm going to go back. I'm opening exercise 2. That's really what I want to start off with. Okay, sorry for the confusion there, but I'm going to open up exercise 2 instead of exercise 1. Okay, so first problem. The mean SAT score for a population of first-year students at Hunter is 620. The standard deviation of scores in this population is known to be 95. So we know the population mean, first-year students, and we know the population standard deviation. An investigator believes that the mean SAT score for first-year psychology majors is significantly different than the mean score of the population of the rest of the first-year students. The mean of a sample of 36 randomly selected students, first-year psychology majors, is 648. So we want to know whether the true population mean for psychology majors, we only sample 36 of them, is different than that 620. That's called a single sample t-test. We're going to look for our 95% confidence interval, and we're going to look to see if that 620 is outside of that interval. Okay, that's kind of the way the t-test is going to work. It's a little bit different in calculation, but we're going to get into that later on. Okay, test 95, state the null and alternative hypotheses. Okay, so now the first thing I'm going to do here is I'm going to say to myself, for the purposes of this first calculation, that we know that we're going to assume that the standard deviation for the population of psych majors is the same as the standard deviation for the rest of the population, 95. We're going to assume we know sigma in this first case. Okay, so let's state our null and alternative hypothesis. A lot of times the way that we simplify that is H with a 0 and a slash through it, or just typing in H null. Okay, so my null hypothesis is what? My null hypothesis is that the two of them have the same mean. Okay, in other words, that the mean for the all students is equal to the mean for psychology students. Okay, that's my null hypothesis. My alternative hypothesis, in a lot of ways we might state that, is H alt, is that the mean for all students does not equal the mean for psych students. Okay, simple enough, right? Okay, so now let's notice something here. Did I predict whether the mean for psych students is going to be greater or less than the rest of the population? I just said it was different, right? So this could go either way. Psych students might have a lower mean. Psych students might have a higher mean. I'm not predicting that in advance here. This is called a two-sided hypothesis test. Why is it two-sided? Because I'll be satisfied with proving it in either direction, proving that psych majors have a lower mean SAT test or proving that they have a higher SAT test. Doesn't matter to me whether it's higher or lower. Either one of them is okay for me to reject the null hypothesis. Okay, I'm only interested in proving that there's a difference. I'm not making any assumptions about whether the difference is one way or the other way. Okay, so let's take a look at this. Okay, so so now let's look at this from the perspective of our 95% confidence interval. If I want to calculate a confidence interval for my sample of 36 randomly selected students, first thing I have to do is calculate the standard error because it's a sample. So the standard error is going to be equal to, what's going to be equal to? It's going to be equal to the population standard deviation, which was 95, right? Divided by the square root of the sample size. 36 is the sample size, so that's divided by 6. So, okay, so what's that going to be equal to? Let's get a calculator out. 95 divided by 6 is equal to, I'm going to call it 15.8. Okay, so now I'm going to calculate a 95% confidence interval for this value. Okay, so my 95% confidence interval is going to be equal to, let's see, it's going to be equal to the mean, which is 648, plus or minus, and what am I going to add and subtract that? I'm going to add and subtract the margin of error. And how do I calculate that? I use the t-score. What's the t-score for a sample of size 36? I'll tell you what. I'm gonna let us cheat this time around. I'm gonna say since it's a sample that's bigger than 30, I'm gonna, for this one instance, I'm gonna say let's use. And actually, I don't even really need to calculate that because what did I tell you? One of the assumptions that we can make was that the standard deviation was the same for the two populations, that we knew sigma. So I don't really need to use a t-test here. I can use 1.96. 1.96. My real justification is that we know or assuming we know the population standard deviation. My cheat is that it's a large sample. It's bigger than 30 a sample size. So I might allow myself to use it anyway. Okay, so 1.96 times the standard error, which is 15.8. Okay, so let's calculate that. What's the lower side of that? Get my calculator out again. Okay, first thing I'm going to do is calculate. Let me clear memory here. Okay, is going to be 1.96 times 15.8 is equal to this. See, normally I would tell you don't round at this stage. You shouldn't have rounded the 15.8 because now I'm multiplying it by 2 basically. So I'm doubling the error. So that's usually why I would tell you not to do that. I would say roughly 31 or 30.968. I'm going to put that into memory. Oops. Memory plus. I'm going to clear this and I'm going to say 648 minus 30.31 is going to be 617. And the upper limit is going to be, let me get that back again. Maybe it's easier if I do it this way. Good. Yep. Clear. 648 plus, recall that, 670, I'm going to call it 679. Okay, so we're 95% certain that the true population mean for psych students with 95% certainty is between 617 and 679. Can I say with 95% certainty that that's different than the rest of the population, which was 620? What do you think? Can I reject that idea? No, right? Because I would be, that 620 is within the range that I would say that, that I have less than 5% chance of that population being outside that range, right? I really don't get the feel for this, that like really that they're different, right? I would have been much more comfortable if the 620, the population that I know, is outside of that confidence interval that I have for the population I'm comparing it to, right? Can you get a sense for that? that like because it's within that interval, that I'm really not sure that the two of them are different, at least not with the level of certainty that I want, right? Let's do this a little bit differently. This time, instead of looking at it from the perspective of a confidence interval, I'm going to calculate a number of standard deviations that these two groups are apart, these two means are apart. Okay, so let's take a look at how I might do this. Okay, I'm gonna say that that there's a couple of ways I could refer to this as a t-score, a z-score, because I know the population standard deviation. I'm going to say that the number of standard deviations, and we know that z and t really represent the number of standard deviations that two samples are that your samples are apart, right? Isn't that really what z stands for? Number of standard deviations. Okay, so I'm going to say that that number of standard deviations is going to be equal to, whoops, I want to put a lower t in there. What is it? A word that doesn't like lower t's at the beginning of a line. T is equal to, and what's it going to be equal to? Well, you remember what it was before? It was x minus mu over the standard deviation, right? Okay, so let's see. What is x and what is mu? Well, in our case, x is our 648, our average for our population, minus mu, which is the mean that we know, right? Which is the value we're comparing it to, with 620, right? And I'm going to divide that by the standard deviation, which we decided was, or actually standard error, which we decided was, what was the standard error again? 15.8, right? Okay, so let's see. I'm going to put parentheses around these two. Okay, so what is that equal to? That's equal to, is a difference of 28 between these two, and I'm going to divide that by 15.8. Okay, and that's going to be equal to, let me get my calculator, 28 minus 15.8. That's going to be, whoops, that's obviously not true. 28 divided by 15.8. That's equal to 1.77. Okay, I'm going to write that down, 1.77. How many standard deviations would I want them to be apart to be able to say with less than 5% chance that these two are not really the same, that they're really different, that my likelihood of getting that big a difference is going to be enough for me to reject the idea that the means of the two groups are the same? What does your instinct tell you that that number would have to be for 95% certainty? Yeah, just your instincts. What do you think? What number comes to mind? 2, or better than 2, more accurate than 2. 1.96, right? Because you associate that with 95% chance certainty and with 5% chance of being wrong. This is 1.77. Okay, well, let's take a look. Let's pull up a page here that we can write on. Let's take a look at that graphically. Let me get in here. Let me see if I can't find it. There it is. Good. Oh, gotta plug this thing in. Where'd it go? Let's look at this in terms of like samples, how samples are distributed. Okay. So now I'm going to assume for a second that I have a normal population, and I'm going to take repeated samples of size 36 from that population. I would expect that the means of those repeated samples are going to be distributed. I'm actually going to make believe it was. It would have been more elegant for me to do this the other way around, but I'm going to do it 648. Okay, I'm going to use 648 for my mean. Okay, now we said sigma, the population standard deviation, was 95. So if we take samples of size 36, right, that would tell us that our standard error is going to be, how much was it? Was 15 point something, 15.8. Okay. And we would expect that if I took samples of this size, that the average for those samples would be distributed so that approximately 95% of those would be within two standard deviations, actually 1.96 standard deviations below that average, below the average for that population, and 1.96 standard deviations above the population for that. Okay, so now let's say that I went and took another population, and I sampled that other population, right? And I found that the value for that population, the mean that I found for that population, that sample that I took, wound up being down here, a z-score, a t-score or a z-score of 1.77, negative 1.77, right? That would be the number 620, right? Well, in order for me to say that, the rule that I've made for myself is I want to be 95% certain, or I want less than a 5% chance of being wrong. Right? What do I call that 5% chance of being wrong? Anybody remember what kind of error that is? That's a type 1 or alpha error, right? I want less than 5% chance of being wrong if I say these two groups are different from one another, right? So the means of these two groups are different from one another. In order for me to achieve that, I have to be outside of this range where 95% of samples from this population would wind up being. So I'd have to be further away than 1.96 standard deviations below and 1.96 standard deviations above. Okay, what percentage of the samples from this population would be less than 1.96 standard deviations below? What's that area down there? That's 2.5%, right? And the area above is 2.5%. So the total percentage of times that I would get a sample from a population that's the same, the total percentage of times that I would get a sample that would be beyond, but lower than 620, or lower than 1.96 standard deviations below and higher than 1.9 standard deviations above, the total amount of time that might occur is 5% of the time. So if I'm outside of that range, that's something that would occur less than 5% of the time if the samples were the same, two populations were the same. So I'm going to make a rule that if they're outside of that, I'm going to reject the idea that they're the same and say that I have enough certainty that to say that they're different, to reject that idea that they're the same. Okay, are you always going to be right? No, you could get, even if you're out here, well, 1.5% of the time, 1.5% of the time that you sample two populations that were the same, if you're all the way out here, that you could wind up falsely rejecting the hypothesis, making an alpha error, right? But you're willing to accept that because you want to make this something that in a real world situation you can at least predict, but predict with at least this level of certainty, right? I mean, we could instead choose to be 99% certain. Alpha error is 1%. We could choose to be 99.9% certain, but we would need much larger studies, much larger sample sizes to be able to demonstrate that. So much of the time you'll see in studies that they're looking for an alpha error of less than 5%. They're satisfied with that level of certainty. And what happens every once in a while? Every once in a while you have a study that's published that demonstrates something like this that someone else tries to replicate and can't replicate it. So it does happen that you falsely reject incorrectly reject a null hypothesis occasionally. But at least you have an understanding of what the probability of that occurring is going to be. Okay, so what was our t-score? Negative 1.67, 1.77. Is that a big enough difference in standard deviations and t-score for you to reject the null hypothesis, to say that the two populations are different? No, it's not. How big does it have to be? 1.96 above, below at least, or 1.96 above. So if I go back here, right? If I go back here to what I was looking at, what I was doing before, okay? Our null hypothesis is that the two means are the same. Can I reject that null hypothesis now? No, I can't, right? Okay, so that means that the mean, the null hypothesis is true and that the mean for everybody is the same as the mean for psych students. Is that correct? That's not correct either, right? Because I haven't proved that they're the same. All I've done is fail to prove that they're different. I didn't have quite enough data. There wasn't quite a big enough difference between these two means for me to reject that null hypothesis. So what happens? I fail to reject the null hypothesis. Okay. So another way that I could have written this is I could have said that the mean for psych students is equal to 620, which is the mean for all students, right? Just substitute that value for it instead of just using the term mu for all students, right? There's a couple of ways I could have done this, okay? Or that the mean for psych students is not equal to 620. Basically, I'm stating it the same way since I know the population mean that I'm comparing it to is 620. This is called, what is it again? A one sample t-test. Why one sample? Because we're comparing a known value in one population, the mean of one population, to a sample that we have of the other population. Okay, so only one of the two groups is actually sampled in here. Okay, let's take a look at the next one. Okay, the mean SAT score for a population of 6 boys looks familiar, right? Standard deviation is 95. An investigator believes that the SAT first year is significantly different. The mean of a sample of 25 randomly selected first year psych majors is 648. Okay, test the above claim, 95% confidence interval. Nothing's changed here, right? Still the same null and alternative hypothesis. We're going to calculate standard error. We're going to do the t-test again. We're going to state our conclusions. The main difference here is that in this case, we have a small sample size, only 25, and we don't say that we know that we're not making the assumption that we know the standard deviation of the psych majors. So our only source for the standard deviation of psych majors is if we actually calculated it. In this case, they only gave us the population standard deviation, so we're going to say that we know it, and we could use still use the z-score. It's a small for a small sample. Let's skip over this one. Take a look at the next example. The mean number of close friends for populations for a population of people living in New York is 5.7. Okay, what's that? In other words, you'd list how many they surveyed people. How many close friends do you have? I presume, gave them a definition for what's a close friend. The mean number for people living in New York is 5.7. The standard deviation in this population is known to be 1.3. However, they wound up knowing it. An investigator predicts that the mean number of close friends for introverts will be significantly different than the mean for the population. The mean number for those close friends for mean number of close friends for a sample of 26 introverts turns out to be 6.5. Does this support the investigator's prediction? Okay, what's his prediction? His prediction is that it's going to be different for introverts and for the rest of the population, right? But we don't usually state things that way. How do we start here? We start with the assumption that the two groups are the same. So what's our null hypothesis? Our null hypothesis is going to be that the mean for everybody is the same thing as the mean for introverts. Okay, what's our alternative hypothesis? Mean for everybody is different. Okay, I'm going to talk about that in a second. It's different for the mean for introverts. Okay, so let's talk about that for a second. What is this guy predicting? This guy is predicting that introverts will be significantly different. He didn't say that it's going to be higher or lower, just that they're different. So we've represented this with our null and alternative hypothesis, right? Again, a two-sided test, right? In other words, it could be lower, could we're not making any assumptions about whether our sample group is higher or lower than the mean that we're comparing it to in the other population. Still going to be a two-sided test, meaning that our 5% is going to be divided up into 2.5% on the low end of our distribution, normal distribution of samples, and the high end of our normal distribution of samples. And if we know our population standard deviation, that the z score that we're looking for them to be apart is going to be 1.96. Okay, so now they didn't tell. We don't know what we know the population standard deviation for New Yorkers is 1.3. The mean for, let's see, the mean is 6.5. Okay, so now let's say that we make the assumption that the population standard deviation is the same for both groups, that we know sigma. Okay, if that's the case, let's do these calculations if that's the case. So our standard error is going to be equal to, well, let's see, do you see any other standard deviation there? No, no, that doesn't. But yeah, I meant that to be that. Like that's the only that's known. Standard deviation and okay, and mean, and I could add that and is assumed to have the same standard deviation as the population. How's that? Okay, good. I think in the next one, that next 2A is going to be the same thing without that assumption. At least that I'm hoping. Okay, so at any rate, so let's calculate standard error. What's standard error in this case? Oh, you already figured it out, really? Standard error is going to be equal to, what was the standard deviation? Is 1.3 divided by the square root of the sample size. The square root of, what's the sample size? 26. And what does it come out to be? Right? It's not 4.5, right? Clear. 1.3, let's see, square root of 26. 26. Square root of 26 is that. And 1.3 divided by that is 0.25. Okay, it's 0.25. So the standard error is equal to 0.25. Okay, and so now if we wanted to calculate a confidence interval, we would, since we know the population standard deviation, we would say that the confidence interval is going to be equal to the mean plus or minus the 1.96, we know, since we know sigma, times the standard error, okay, which would be about half added and subtracted from the mean. So instead of that, let's calculate the number of standard deviations that this sample is from the known value. So t is going to be equal to, again, t going to be equal to, it's going to be equal to x minus mu, right? Okay, so x in this case, let's use x as our sample mean, which is, what was our sample mean? 6.5. Or actually, let's use the, either way, 6.5 minus 5, what was it, 5.7 divided by 0.25. Our standard error. So what is our t-score? How many standard deviations apart are these? What is it? 3.2. Okay. They're 3.2. Now I could call this, instead of calling this t, I could call this z, right? Because in this case, we know the population standard deviation. So if I look at my normal distribution, if these things are that far apart, I'm going to call it 3 standard deviations instead of 3.2. Okay, if I look at this, and here's our mean, and the value that we just checked against was 3 standard deviations away, right? What's the likelihood of getting a value for a mean from a sample of that size, getting a value for a mean that's as much as 3 standard deviations away?
It's 7 o'clock.
What is the area that's left here? How often would that occur if they're really the same, if they're really in the same population, 2 populations are the same? How often, what percentage of the time would that occur? Well, where can we look that up? We can look that up in the Z table, right? So let's look it up in the Z table. Oops. Okay, so in the Z table, get this out of the way. If I look in the Z table, well, remember, the area that's above a Z-score of 3 is the same as the area that's below a Z-score of -3, right? Those 2 areas are the same. So I can just look over here to -3, and I can see that 0.013, about 1.3%, 0.013 or about 0.0013 or about, actually 1/10 of 1%. 0.0013 or about 1/10 of 1% is below a z-score of 3. And that means that the same amount is above a z-score of +3. So this area on either end, remember we have a 2-sided test, so we didn't make any prejudgments about whether that 3 was going to be a positive number or a negative number. This is 0.0, I'm going to call it 0.001. So this area is 0.001. So in order to get a score, these 2 means that are that far apart, how often would that occur if they're from the same population? Well, I'm going to add the 2 of these together. And it's going to wind up being, my probability of that occurring is 0.002. Actually, it was 3. I'm going to actually add that. 0.0026, right? About 1/4 of 1%. Okay. Is that probability less than my acceptable alpha error? What was my alpha error? My alpha error was I wanted it to be less than 0.05. Is P less than 0.05? Sure it is, right? It's much smaller than 0.05. So what does that mean about my null hypothesis this time? Can I reject it and say that it must be, we think it's from a different population? What do you think? Right, because the probability of getting an outcome where the 2 means are that different would only occur 1/4 of 1% of the time, right? Less than 5% of that I would accept as a possible amount of times that I could be wrong. So in this case, what do I do with the null hypothesis? Okay, in this case we reject the null hypothesis. Hypothesis. And well, what else can we say? If we reject the null hypothesis, what are we doing by default? We're accepting the alternative, right? If we reject the null hypothesis, we're basically just accepting the alternative hypothesis. Okay, so we're accepting the hypothesis that the 2 groups are different, have different means. Okay, before we were not able to do that. We failed to reject the null hypothesis. Why? Because the 2 means were not far enough apart to have that level of certainty that I wouldn't get that outcome by chance. Okay. Make sense? Okay, let's throw a little twist into this. We've been working with sample sizes that are big enough, or working with knowing that what the